Okay, so I have started the recording. First, let's look at the checkpoint of last time. And this was the question. Okay, so in order to answer this question, I think it's useful to think back about the trace route, right? Because the trace route is what we run to measure the actual delays on the internet. And if you remember the trace route we run in class, well, first there was the case where when we went to Europe, we saw that there was a sudden jump of about 100 milliseconds, and that was caused by the going over the undersea cable. And because the undersea cable is a very long link, that caused a very large propagation delay. Okay, so there was at least one instance where the propagation delay was the primary contributor to the end-to-end delay. But there were also some other measurements, like before. So in the first few routers, before we went over the undersea cable, where we saw that there can be a lot of fluctuations from one probe to the next, even though the probes are sent to the same router. And then we had that discussion on Piazza that where I explained that, okay, so these fluctuations, they are caused by the queuing delays. And we even saw a case where because of the queuing delay, the round trip time for router 3, if I remember correctly, was greater than the round trip time for router 4. So that was another example where, in this case, in this example, the primary contributor was the queuing delay. Okay, so given that you have these choices, and given that, okay, we had a case where the queuing delay was the primary contributor, another case where the propagation delay was the primary contributor, I think that gives you a strong hint that the correct answer is that it depends on the circumstances. Okay, so if you have a short packet, transmission delay is not going to be a primary contributor, right? If you have a short packet, a very long distance, but then it will be propagation delay. If you have a lot of congestion, no sound yet. Okay, can you hear me? Raise your hand if you can hear me. Okay. All right, quite a few can hear me. Let me send a chat to the student. Okay. All right, thank you. You can lower your hand. Thank you. Okay, so I was saying that it depends on the circumstances. If you have, for example, a lot of congestion in the network, let's say you have a short packet, so the transmission delay is not going to be a significant contributor. If you have a short distance, propagation delay will not be a significant contributor. But if you have a lot of congestion, then queuing delay will be the primary contributor. Any question on this one? Okay, if not, then let's start a new unit. Okay, I don't know what part you missed, but I'm going to repeat. Okay, let me. Okay, I was simply saying that, well, first, the correct answer is D. It depends on the circumstances. Because let's take an example. If I send a short packet, let's say I send a short packet over a very long distance, but the network is very lightly congested. So in that case, because the transmission delay is equal to the packet size divided by the transmission rate, if a packet is short, transmission delay is not going to be significant. If it is long distance, a propagation delay will be significant. If the congestion level is low, then queuing delay will not be significant. So in that case, the propagation delay will be the primary contributor. Now, let's take another case. If I have, again, a short packet, but now if I send over a short distance, but my congestion level in the network is high, then transmission delay and propagation delay will not be significant, but the queuing delay will be significant because of the congestion. Okay, so I just gave you two examples, and that shows clearly that you cannot make a general statement about which delay is the primary contributor, right? It depends on the circumstances. So does that answer your question? And actually, if you think back about what we saw in the trace route, that was the case, right? We saw some instances where it was the queuing delay, and then we saw other instances where it was the propagation delay. Okay, so now let's start the next unit, which is Unit 7. James, I see that you have your hand raised. Do you have a question or not? Okay. Right, transport layer. So now we are done with the application layer. We are now going to move down one layer and look at the transport layer. So the transport layer is the job of the transport layer is to provide communication between. Okay, let me activate the pointer. So the job of the transport layer is to provide communication between application processes which run on different machines. Okay, so here I have some application process that needs to communicate with another application process here. So they are on different machines. And in order to do that, the application process will use the services of the layer below, which is the transport layer. And the transport layer resides at the two end systems. Okay, so here, this end system, and here at this end system. There's no transport layer in between. Okay, now let's look at what happens at the sending side. So the sender, when the transport layer will receive data from the application process to be delivered to the other application process. And in order to do that, the transport layer may need to break the messages, the application messages, especially if they're very large messages. You have to break these messages into segments. Okay, so when we hear segment, that refers to a packet at the transport layer. Now, the transport layer itself will use the services of the layer below, which is the network layer, in order to do its job. So after they've done that kind of breaking the message into segment, it will hand over the segment to the network layer. And then the network layer will do its job, which is to deliver the packet at the destination host. And then it will deliver to the transport layer at the destination. At the destination, at the receiver side, the transport layer will reassemble the segments in order to rebuild the original messages that were at the sending side, and then hand over these messages to the application process. On the internet, there are two main transport layer protocols, which are TCP and UDP. Okay, so now the transport layer sits between the network layer and the application layer. So in order to do its job, it will have to use some algorithm and techniques to meet the transport requirements. Remember, depending on the type of application, we may have a different set of requirements, right? So for example, some types of application have a requirement that all the data need to be reliably delivered, right? No loss, no duplication, no misordering. Some other types of applications may require to have a low delay. Okay, all these various type of things. So these are the transport requirements, the requirements that are put on the transport layer that are imposed on the transport layer by the applications. And as we know, as we have seen last time, essentially there are two types of services provided by the transport layer. So one is the connectionless, unreliable datagram, which is provided by UDP. And the other one is reliable byte stream, which is provided by TCP. Now, in the case of UDP, it is connectionless, meaning that you can send the data without having to set up a connection. And in the case of TCP byte stream, it is connection oriented, meaning that before you can send data, you need to set up a TCP connection. Okay, now the transport layer uses the services of the network layer below. So it will be subject to the limitation and constraints of the network layer. So here we already know one type of limitation, which is that packet may be lost, right? So when the buffer is full, then the packet will have to be discarded by the router, and therefore you will have packet loss. So that is an example of limitation of the network layer below. But there can also be other type. Okay, question in UDP, it is not sent in byte form. Okay, so essentially everything is bits, right? We're dealing with computers, so everything is bits. But when the application process sends data to a UDP socket, so let's say, for example, if the application process sends 5 bytes to the UDP socket, these 5 bytes will be handled like a packet. Okay, so you still have the concept of bytes, but each time the application process sends a group of bytes to the UDP socket, that will be construed as a packet. In the case of TCP, the application process also sends bytes, but let's take an example. The application process may send, for example, bytes 1, 2, 3, and then pause a little, and then send another group of bytes, which is 4 and 5. Okay, 1, 2, 3, and then 4 and 5. So it could be that TCP will decide to TCP will also put all these bits into packets, but these bytes 1, 2, 3 will not necessarily correspond to a packet. it could be that TCP will send a packet which consists of byte 1, 2, 3, and 4, 5. Okay. All right. So underlying physical. So there's also another type of limitation, other types of limitation, which we'll look at in more detail later in this class, which is that the bits that you send may be received in error. And what that means is that you send a 1, but it is received as a 0. Or you send a 0, but it is received as 1. And that is referred to as the bit error rate. Okay, bit error rate. So, for example, if we 10 to the minus 6, that means on average, for every 10 to the power 6 bits, you will have 1 bit in error. And that tends to happen in wireless communication. So things like Wi-Fi, cellular communication, you will have bit errors. That would tend to happen more, right, when you have wireless communications. Okay, so you have the transport layer has to deal with these limitations of the network layer. But on the other hand, coming from the application layer, it needs to meet quite a few types of requirements. And here we have some examples. Okay, so quite a few requirements. All right, so the transport layer is kind of caught between the rock and hard place, right? It has these limitations of the underlying layer, so you can have bit errors in the message. The message may be lost, the message may be delivered out of order, and the message may be duplicated. And that will happen at the network layer. Also, the packets have a maximum size, right? Maximum size. So if the application process has a very big message, the transport layer will have to do the breaking down into segments so that it will not exceed the maximum message size of the layer below. Okay. As an example, if we run over Ethernet, the size is about 1500 bytes. Okay, so this is essentially the statement of the problem. We have a transport layer. It needs to meet these requirements put upon it by the application layer. But in order to do its job, it will use the services of the network layer and the layer below, which have these limitations. So we're going to take like a one step back and look more broadly at the transport layer services. Okay, so what kinds of services a transport layer may provide? So first type of service is multiplexing, demultiplexing. Another type is reliable data transfer. Another type is flow control. So reliable data transfer, essentially it's a service where the transport layer will guarantee to the application layer that the data will be delivered without loss, in the right order, and without duplication. Flow control means that the sender, the transport layer, the sender at the transport layer will not overwhelm the receiver. Okay, so it will adjust its sending rate so that it will not overwhelm the receiver. And then congestion control means that the sender at the transport layer will adjust its rate to minimize the congestion in the intervening routers. Okay, so we will learn about the principles. So these are kind of general concepts, if you wish, about the transport layer. But we will also learn about specific protocols, transport layer protocols used on the internet, which are UDP, which stands for User Datagram Protocol, and TCP, which stands for Transmission Control Protocol. And we also spend some time on the TCP congestion control. Okay, now I think it's useful to clarify a bit what is the difference between the services provided by the transport layer and the services provided by the network layer. So the service provided by a network layer is to enable communication between hosts, between machines. The transport layer goes beyond the communication between hosts, because it enables communication between processes within hosts. Okay, so it builds upon the service provided by the network layer. So let's take an analogy with a household. Let's say that Anne lives in a house with 12 kids, and Bill lives in another house with also 12 kids. Okay, now each of these kids may be sending letters to another kid in the other house. So in this analogy, a host will be a house. Okay, a host will be a house. A kid is a process within the host. Okay, so here we have 12 kids in each house. So each of these kids, each of the kids is an application process. Each of the kid may want to send data to another kid in the other house. Okay, so that message, which is an application message, is a letter. The kid wants to write a letter, right? That in an envelope. Okay, so now the kids are in the application layer. They essentially, a kid wants the letter to be delivered to some other kid in the other house. So in order for that to happen, it will use the services of Anne or Bill, depending on which house they are in. Okay, so Anne and Bill, they will provide the transport layer services. And what they do is that they provide that demultiplexing service to their siblings. And in this analogy, the network layer is the postal service. So what happens is the postal service provides a service where they deliver a letter from one house to another house. The postal service does not deliver a letter to a specific kid, right? They just deliver the letter to the mailbox of the house. So you can see that there's one more step that is missing, which is once the letter is delivered to the mailbox, how would that letter reach the kid? And that is done by Anne or Bill, which are the transport layer. So Anne and Bill, they go go to the mailbox. They pick the letters from the mailbox, and then they do that additional job, which is the delivery of the letter to the destination kid. And that corresponds to demultiplexing. Okay? Any question? So Anne and Bill, they're also, because in this case we use the services of the postal service, we are also, the transport layer also constrained by the limitation of the postal service. So if it is a regular mail letter, that letter may be lost, right? Okay. Okay, question is transport layer physical or logical or both? So transport layer is, I'm not sure what you mean by physical, but anyway, it's a set of functionality and it is implemented, right? So typically it is implemented in code. So I don't know, I'm not sure what you mean by physical or logical. So it's a set of function that you implement with code, some software. Okay, so if we look at the transport layer, they reside at the two end systems. Okay, then we have the first type, which is TCP, reliable in order delivery, and it provides this. It has these three attributes, and we have the other type UDP, which is unreliable. Now, regardless of whether it's TCP or UDP, there are some things that cannot be guaranteed by the transport layer, and these things are the delay. So no matter what service you use, TCP or UDP, the transport layer will not be able to guarantee that the data will be delivered within, let's say, 1 millisecond. Okay. Another type of things that cannot be guaranteed is bandwidth or throughput. So the transport layer cannot guarantee that the throughput will be, let's say, at least 100 kilobits per second. Say. Okay, I'm sorry about the background noise. It's lawn mowing. Actually, I think that bothers me at least as much as you, but I have no control over it. Okay, let's look at the more detail about multiplexing and demultiplexing. So here we have a server, we have a client, and we have another client, and we have the sockets and the processes, right? So at the sender, there's the multiplexing that takes place. So here there is data coming from this P1, the process P1 that goes to the socket, data from process P2 that goes to this other socket. Now the transport layer will receive all this data coming from the sockets, and then it will need to do the multiplexing. And in order to do that, it will need to add a transport header to the packet. And that transport header will later be used for demultiplexing at the destination. Okay. All right. So this is at the sender. Now, if we look at the server as a receiver, because the server is sending data, but the server is also receiving data. So it will receive data from these two clients. And in the data that it receives, there is the transport layer header, which was attached by the clients, right? Because the transport layer of the clients, they also add a transport layer header. So that transport layer header will be used by the transport layer at the destination to determine what is the right socket to deliver the data to. Okay, so that is demultiplexing. Okay, demultiplexing, essentially you have a bunch of data packets coming into the host. Now, it has been delivered to the host, but the job is not complete. It needs to be delivered to the process. And for that, demultiplexing has to take place so that it gets delivered to the right socket. and once it's delivered to the right socket, it is delivered to the right process, okay, because the process is associated with a socket. Okay, so now question, how does the demultiplexing work? In other words, what kind of information will be used by the transport layer to do the demultiplexing? So if we look at the transport layer header, this is first, there are two services, right? There are two services. We have UDP protocol and we have TCP protocol. So depending on the protocol, you will have a different transport layer header. However, regardless of whether it's TCP or UDP, the transport layer header will always begin with the port numbers. Okay, so that is what we see here. This is a transport layer header, and the first 32 bits will be, actually the first 16 bits will be the source port number. The next 16 bits will be the destination port number. And that is true for both TCP and UDP. And then this part is the payload, which is the application data. Okay, so for an example of application data could be the HTTP request message. The HTTP request message would be carried here in the payload. And then there's added to it will be a transport layer header. Okay, so this is this format where you have a source port number, 16-bit, and a 16-bit destination port number is common to TCP and UDP. And the result, so the transport layer receives the application message, will add this transport layer header. And the result is the segment. This whole thing is called a segment. Okay, now let's look at how the multiplexing works. So the host will receive these datagrams, which have the, in addition, so this is not shown here, but a datagram will have also an additional header, which is a network layer header, which is not shown here. But in the network layer header, there's a source IP address and a destination IP address. So essentially, that information identifies the source host and the destination host. And each datagram will carry one transport layer segment, which is this segment here. And each segment has a source port number and a destination port number. And now the destination host will use the IP address information and the port number information to direct the segment to the appropriate socket. Okay, so this is demultiplexing. Okay, let's first look at demultiplexing for UDP, which is connectionless. So remember, when you created a socket, when you create a socket, a UDP socket, the socket has an associated local port number. Okay, so that is from the lecture of last time. Okay, now when you create a datagram to send it to when you send data to a UDP socket, you must specify every time you send a datagram, you must attach the destination information, which is the tuple, destination IP address, destination port number. Okay, so this is what we have seen last time. Okay, so this is the sending side. What happens at the sending side? At the receiver side, when the host receives the UDP segment, so think packet, the host will check the destination, look at the destination port number in the segment. And that destination port number will determine the destination socket. Okay, because remember, each socket has a port number. So destination port number will identify the socket. Now, the implication of that is that you may have packets or IP datagrams with the same destination port number, but coming from different hosts, right? For different source IP address, or it could be also different source port numbers. But because it only looks at the destination port number to deliver to the socket, all these packets, they will be delivered to the same socket at the destination. The only piece of information that is used to identify the destination socket is the destination port number. And that is how connectionless demultiplexing works. Let's look at this example. Here we have a UDP socket, and we create it. So here we have a client. This is a server. Remember, when we create a socket at the client, the operating system will choose the port number for that socket. In this example, this is the port number that was chosen by the operating system, and it will be associated with this socket. Same thing here on the other client. This is the port number associated with this socket. At the server, when we create a UDP socket, here the port number is this one. Okay, so every socket has a port number associated with it. Okay, now let's say P3 wants to send data to P1. It's going to push the data to this socket. Now, because it's a UDP socket, it needs to attach the destination information. And the whole thing gets sent to the server. So if we look at the port number, so remember the transport layer header has the source port number and the destination port number, right? So the source port number will be this port number because it's coming from this socket, which has this port number. The destination port number will be this one because that is the socket we want to send the data to. So we just put the corresponding port number. Okay. So this was the destination port number was attached by P3, right? So P3 gives the data to the socket and tells the socket, I want to send to this destination port number and also this IP address, which identifies the host. Okay, this gets sent, it gets received here. At the destination transport layer, it does demultiplexing, and in order to deliver to the proper socket, it will just look at the destination port number, which is this one, 6428, and it will deliver to this socket because that is the one which has this port number. Okay, and then if the server wants to send a reply, then it will work the same way. That is P1, again, because this is a UDP socket. So P1 will need to attach the destination information. In this case, it's going to be destination IP address, which is the IP address of this host, and destination port number, which is 9157. And the source port number, in this case, will be this port number. And remember in the case of UDP socket, when P1 reads the data coming from the socket, it's also able to extract the source information. In other words, where is the data coming from? So it will know that it's coming from this IP address and it's coming from this port number. So that is what will allow the P1 to reply, because when it sends the reply, it will need to attach that information, but this time as destination, right? So this time destination will be this IP address, and destination port number will be the port number that it read when it received the data, the destination port number. Sorry, the source port number, right? So it read 9157, and it knows that, okay, now it wants to reply to P3, so it will put as destination port number 9157. Okay, so now quick question for you. Let's say that P1 wants to send data to P4. So we'll push data to the socket. So here note that it's the same socket, right? This same socket is used for communication with P3 and P4. So when it pushes data to this socket, now it needs to tell the socket what is the destination. So here you can see clearly why we need to every time specify the destination, because when P1 pushes data to the socket needs to know which is the destination, because there could be any socket could be the destination. So in this case, when it gets sent by P1 to P4, quick question for you: what should be the source port number and what should be the destination port number that is carried in this packet in the transport layer header? Let's start with the source port number. What is the source port number? Yes, the source port number is this one, right? The socket where it's coming from, and the destination port number is 5775. And then when P4 replies, it should just swap, right? You just swap the source and the destination. Okay, I think you get the idea. So connectionless demugs is what happens with UDP. And you can see that with the UDP sockets, it's not a one-to-one mapping between sockets. Here you can see clearly this socket can communicate with many other sockets. One-to-many, right? Not one-to-one. Okay, now let's look at the connection-oriented multiplexing, which is what happens in TCP. So now pay attention. TCP is a bit more complex, and a TCP socket is identified by a for tuple, and we'll see shortly why we need a for tuple. This is the for tuple: the source IP address, source port number, destination IP address, destination port number. Okay, so we need the addresses and port numbers of both endpoints. And to do the demultiplexing at the receiver, the transport layer will need to use all these four values, all the four values in the for tuple, in order to deliver the segment to the appropriate socket. So this is different from UDP, because in the case of UDP, you only need to use the transport layer only needs to use the destination port number. In the case of TCP, it will need to use all these four values. We'll see why. Okay, so if we have a server host, it may support many simultaneous TCP sockets. Remember the diagram we saw last time with the TCP connections, with the welcoming socket and the new sockets, right? So these each of these new sockets is a simultaneous TCP socket, and each of the new socket is identified by its own for tuple. Okay, and also the web server, they have different sockets for each connecting client. So that is again the new socket that we saw last time. And if it is a non-persistent HTTP, then it will need to remember for each request for an object, you need to set up a new TCP connection, right? Because it's non-persistent. So every time you set up a new TCP connection, you will have a new socket. Okay, so as many sockets as TCP connection. Okay, so pay attention here. This slide is a bit crowded, but actually it's not that difficult if you pay attention. So remember the multiplexing for TCP will use the 4 tuple, right? In order to deliver the data to the right socket, it will need to look at all the 4 values. Okay, let's look at this example. So here we have the client, we have the server, and another client. Now these sockets are TCP sockets, not UDP sockets. And you can see right away, visually, you can see the difference, right? Because when you have TCP sockets, it's really a one-to-one association. This socket can only send and receive data from this socket. Same thing here, right? One-to-one, because it's TCP. Okay, now let's look at this socket, the one here. We know that it's identified by a 4 tuple. So the 4 tuple is a source IP, source port number, and destination IP, destination port number. So if I call the IP address B, this IP address A, and this IP address C, and here I assume that this one, actually I think I didn't put the local port number. So there's a local port number that was associated with this socket when it was created, right? Which is, in this example, 80, because we have a HTTP application. Okay, HTTP application, the reserve value for the port number at the server is 80. Okay, so we can fill out the 4 tuple for this socket. Source IP, source port, so it's B. Port number 80, this is the local port number. Now this socket is mapped one-to-one with this other socket. And this other socket correspond to this IP address A because it resides at this host. So destination IP is A. And here I assume that the port number, the local port number associated with this socket is 9157. Okay, so this is the 4 tuple that will identify this socket. And then I can do the same thing for this socket. I can write out the 4 tuple. Okay. And I can do the same for this socket. I can write out the 4 tuple. Okay, so let's look quickly at what the transport layer header looks like when data is exchanged. So if P4 sends data to P3, then the header will have as a source IP address B, right? It's coming from B. Source port number 80, because the local port number is 80. Destination IP address will be A, and the destination port number will be 9157. Okay, now if P3 sends data to P4, then you just swap the source and the destination. Okay. All right. So now you may ask, yeah, so at the demultiplex, if we look at the demultiplexing, then why do we need 4 tuple? Why do we need all the 4 values, right? And this example shows us why. Because here you can see that it could be, actually let's start with this client. So client set up 2 TCP connections with a server, right? This is one TCP connection. This is another TCP connection. And the port number, so each of these connections has a socket associated with it. Yes, correct. So if you have different IP addresses, you can have the same port number, because what really matters is the topo, is sort of the whole topo IP address port number. Okay, so it could be that actually, example, I assume that at this client, the operating system happened to choose the same value for the port number as this one, which is 9157. And that can happen, right? That will happen. But now you can see, let's look at the case where we have the two TCP connection. Okay, so let me finish this, going through this, and then I will answer your question. Perhaps your question will be answered. Okay, so let's say we have two TCP connections that are set up between these clients and the server. Okay, now here the IP address is the same, right? The IP address is the same. It's C. So the destination IP is the same. It's C. Okay, the source IP is the same because it's B. It's B. It's the same. The source port number is also the same because it's 80, because the application is HTTP. So you can see clearly that we will need that also the port number to be able to differentiate between those two sockets. So between the P5 and P6, the four tuples, they differ by the destination port number. Okay, so you need the destination port number. The first three values are the same. Okay, now another case is why do you need the destination IP? Okay, here you can see the source IP is the same, it's B. The source port number is the same, it's 80. Destination IP is different. In this case it's A. In this case it's C. But the port number may be the same. Okay, so I'll show you two examples where you see that you need these four values to be able to differentiate. Otherwise, here you're not able to differentiate. You need the four tuple. Okay, now let's see the chat. Okay, P4, P5, and P6 share the same port because the transport layer is tracking which server socket. Okay, I think that you found the answer to your question, right, James? Okay, then there's the next question by Andrew. So two different devices are allowed to have the same port numbers. Yes, because they are differentiated by the complete tuple, which is the IP address and port number. So different devices will have different IP addresses. And actually, there's no way you can coordinate the devices, right, so that they have different port numbers. It's impossible, because you may have millions of devices, right? And then how can you coordinate them? Okay, so I hope that with this example, you can understand why, in the case of TCP, we need a four tuple to do the demultiplexing. Any question on the? Oh, so this is how the demultiplexing is done at the server, right? Let's to be complete, let's look at how it's done at the client. Okay, so here we have the same example. We have the same example. the actually, let me see. Yeah, so it's as far as the client is concerned, when it receives the data, you need to know whether it should send to this socket or that socket, right? So if I look at this socket and the other socket, they have the same source IP. They have the same destination IP, which is B. They have the same destination port number, which is 80. But what they differ is in the port number, the local port, the source port number. Okay, that's how they can be differentiated. Okay. Oh, sorry. Thank you. So I was simply saying that between P2 and P3, right? P2 and so the client needs to also do demultiplexing. That is, when it receives the data, it needs to know to which socket it should deliver the data. And in this case, we can also see that we need the for tuple because for both of these sockets, the destination IP is the same, it's B. The destination port number is the same, it's 80. The source IP is the same, it's C. So you need the source port number, which is different between these two sockets in order to be able to do the demultiplexing. Okay, and then I think Andrew said, so here the server has 3 different port numbers. The server has 3 different port numbers. Okay, let me see. Oh, okay, I think you're referring. So, okay, I'm sorry, I need to redo this slide. This for tuple actually refers to this socket. Sorry, let me redo this slide. But yeah, I will redo this slide and then go over it again next time. Okay, this is kind of incorrect here. But the point is remains the same, right? The port numbers, the port numbers at the server, the local port number at the server is still 80. It's the same. What differentiates? What is different is the port number here at the client. Oh no, sorry. Let me backtrack. This is different because here we have a server, we have a client, we have a server. Okay, so my slide is correct. Here we have a client, 2 clients which communicate with a server. Okay. Okay. Now let's go to the next slide. You have a client that is communicating with 2 servers. These clients, right? So this is correct. So you look at the socket. The source IP is B. The source port number is some port number value. Let's say 9,000. Destination IP is A, and destination port number is 80. And then the same thing for the other sockets. Okay, so if we look at the demultiplexing that is done at the client, it works along the same principle. And we can see that, for example, here when it receives, the client may receive data over 2 TCP connection with server C. And the way to differentiate to deliver to the right socket is by using the local port number, which is the source port number. In this case, it's 5001. In the other case, it's 2000. The other 3 values are the same. Yes, clients are allowed to have multiple different port numbers because actually not only they are allowed, but they have to. Because the port numbers are assigned by the operating system. And in the case of the server, most of the time, for example, if it's HTTP application, the port number is not chosen by the programmer. It is you have to use one of the pre-reserved, predefined port number, right, for the new application. So if it is web browsing, the port number value has to be 80. Okay, so I hope that this will clarify. This clarifies a little bit why for TCP we need a 4 tuple. Okay, let's do a checkpoint that we skipped last time. What was that? Hold on, let me see. Five dash one? No, 4-2. Okay, 4-2. I'm going to show you the password for 4-2. Okay, I think it's a good time now to take a break, but we will take a shorter break now because we are a bit behind. We need to catch up. So let's take a 5-minute break and be back at 1:38.